Now, we've been discussing average velocities and instantaneous velocities. And example 1, I think, is a really great point that helps illustrate these ideas, especially average velocities. So, the position of a car after t minutes driving in a straight line is given by this function. So, s of t is a function that's representing the car driving in a straight line. Here it is, t is in terms of minutes, and it's happening over the interval between 0 and 4 minutes. And again, s is pretty much measuring how far in terms of miles, and t is in minutes. Now the goal is to approximate the velocity at time t equals 2 minutes. Well, we know that we have this interval between 0 and 4, and our goal is to find out what's happening to that average velocity at time t equals 2. So from that information, what we can do is actually go ahead and find a few secant lines to kind of help us out in determining what is that average velocity. So we're going to go ahead and find out the average velocity of some different intervals. So for example, let's start out with, well, our target point is happening at 2. So what we can go ahead and do is throw in 2 into the function, and when we do that, we have 1/2 times 2 squared minus 1 over 12 times 2 cubed. And what this will simplify out to be is about 1.33. Now let's go ahead and find the position at some other value, some other minute that we're talking about. Let's go ahead and go with maybe like 4. It's just a first reference. So when we throw that in there, we end up with 1/2 times 4 squared minus 1 over 12 times 4 cubed. And what this actually comes out to be about is 2.6 repeating, so 6, 6, 6, 6, 7. Now, if we're trying to figure out what is the average velocities of these, well, all we have to do is pretty much subtract their y's. It's again essentially finding the slope of these 2 points happening at 2, 1.33333, and then 4, 2.66666. So you're finding just pretty much the slopes of these two items, these 2 points. So then we end up with 2.666. We'll just stop there maybe. We'll do a 7. Minus our 1.3333. Because again, these were the positions or our y values on top. Now we're going to go ahead and do our time on the bottom. Well, our first time, our other point was 4. And our target point is 2 minutes. So then it looks like when you punch this into the calculator, it comes to be about 0.6667 miles per minute. But again, we don't want things in terms of minute. At least usually when we're talking about driving a vehicle, we typically have things in miles per hour. So what we're going to do is just multiply this guy by 60, because there are 60 minutes in an hour. And when we do that, we end up with about a speed going by 40 miles per hour. Again, because we were measuring this time in minutes, so that's why we had to multiply it by 60 to get the miles per hour. So the average rate of change between 2 minutes and 4 minutes is 40 miles an hour. So just really fast graphically, what's going on here is at 2 we have some point, at 4 we have some point, and we have some function that's doing something like this. All right, that's passing through those 2 points. What we've essentially done, and again, here's that function right here. Between those 2 points, we found the average rate of change, that average speed. We haven't found the instantaneous rate though, specifically at, again, this would have been 2, this would have been 4. That's what we're trying to figure out, is what is that average rate of change, the average velocity, specifically at 2. And as a result, that doesn't give us necessarily the best average rate of change. So what we're going to end up doing is choosing an x value that's closer to our target x value or time value 2. So maybe like we would go with, instead of 4, we would go with 3. Let's go ahead then and find the average velocity at 3. Well, luckily we already have our s of 2 value. It came out to be about 1.33, 3 repeating. Now let's go ahead though and throw in 3 into the function. When we throw 3 in there, we end up with 1/2 times 3 squared minus 1 over 12 times 3 cubed. And just for the sake of time, it comes out to be about 2.25. So it comes out to be 2.25. Again, finding the slope between these 2 points. So we have 2.25 minus our target y, 1.3333, all over the x value, 3, from our other point right here, minus our target x value, 2. That'll come out to be about, when you throw that in the calculator, 0.91667 miles per minute. But again, we don't do things in miles per minute, so we have to convert this to miles per hour just by multiplying this guy by 60. So when we multiply it by 60, it comes to be about 55 miles per hour. And so what we saw was when we got closer to our target point, time 2 minutes, we saw that it actually went up in terms of our speed. Like before, when we did 4 minutes, it was at 40 miles per hour, that average. And when we found the average between 2 and 3 minutes, it went to 55 miles per hour. Now, you could keep doing this and keep doing this and keep doing this, but essentially it's pretty much the same thing as when we were looking at things like our secant, which eventually led to our tangent. But to find our average, so our v average, is going to come out to be the position of our particle or car when we have that time 2 minutes, plus some distance away from time 2 minutes, minus our position when we throw in our target point of 2 minutes, all over our other points x value or time value, 2 plus h, in other words, whatever distance we are to the right of 2 minutes, minus our target 2 minutes. And so just simplifying this, we end up with s of 2 plus h minus s of 2 all over h. Now again, it was our hope to minimize h as much as possible, because what h represents, again, is that distance in terms of our time values away from our target time. And we're hoping to minimize that. In other words, we're hoping to get closer and closer and closer to that time 2 minutes. And so what we would do is to take it instead to an average velocity. What we want is instead an instantaneous velocity at 2 minutes. We would then take the limit as h approaches 0 of this function. S of 2 plus h minus s of 2 all over h. So as h goes closer and closer to 0, in other words, as you minimize that distance away from 2 minutes, you get closer and closer to 60 miles an hour. To the tangent slope, which, again, that's our instantaneous velocity that we're hoping for. And again, that would be 60 miles per hour. So again, though, that is example one, just kind of seeing average rates of change or average velocities start to get to be closer and closer to that instantaneous velocity that we're hoping to find, specifically that speed at 2 minutes. Or I'm sorry, that velocity at 2 minutes. But again, that is example one from our 2.1 number 2 set of notes.